Thank you for the introduction and thank you for inviting me to present my research. I will be talking on geodynamic models to investigate regional and intraplate tectonics. And the reason we know now that the it was an animation showing plate tectonics, but we are all aware that new plates form at the mid-oceanic ridges and the old plates subside at the oceanic trenches. And plate tectonics can explain several geophysical and geological phenomena. For example, it has been used to explain the observed seismic anisotropy. It also coincides with the locations of earthquakes and volcanoes, and it can be also used to explain the stress state of slabs and lithosphere. In order to understand plate tectonics, plate tectonics, we look at the different forces that act as the plates move. For example, on the cartoon here, the plates are driven by the forces that are shown here in green. For example, the slab pull, which happens due to the higher density of oceanic lithosphere with respect to the continental lithosphere. The another driving force is the ridge push, which is due to the elevation of ridge with respect to the surrounding oceanic lithosphere, and due to that elevation, there is gravity, buoyancy that drives the plate. In addition to the driving forces, there are also resisting forces. For example, the friction between the plates. So as the lithosphere moves, it is resisted by the viscosity, which is just below the lithosphere, that is the viscosity of the asthenosphere. And it tries to resist the motion of the plate as they are moving. And another factor that resists the plate are the friction between the plates. So if there are two plates that want to move with respect to each other, the lower the friction between the plates, the easier it is for the plates to slide with respect to each other. So the plate tectonics is driven by the buoyancy forces and resisted by the viscous forces, but we understand the plate tectonics using the interplay between these forces. And that's how we understand the surface observables like lithospheric deformation and stress state. As I discussed, the earthquake locations, they coincide pretty well with the plate geometry. So on the right, the gray circles represent the epicenters of earthquakes in the past 20 years. And these earthquake epicenters, if you notice, lie very closely, majority of these earthquakes lie very closely on top of the plate boundaries, which are marked here in red. But there are also some earthquakes that do not lie in the plate on top of plate boundaries, and these are the intraplate earthquakes, for which we do not understand the mechanism. And this is another focus of my talk, that we understand the interplate earthquakes, but the mechanisms for intraplate earthquake remains poorly understood, and it is also unique to the region. For example, we need different mechanisms to explain earthquakes here versus here. And one region I will focus on today is the central and eastern US. So if we look at the hazard map in the US, the high hazard shown here by the hot colors, we see that high hazard on the in western US associated with the plate tectonics is understandable, but we don't really understand very well why we have high hazard or what is the mechanism of earthquake generation in the central and eastern US. So for example, this zone, which is the New Madrid seismic zone, and you all know that, and the Eastern Tennessee seismic zone and the South Carolina seismic zone. So I will use numerical models to understand that. And why I want to use numerical models is because if we look at the rock record in time, which is shown here in the horizontal axis, so as we go from 4.5 billion years old to today, we have rock record near the surface. We also have geophysical data in the present day. So if we go from surface to the depth, we have seismological data that can help us image the interior of the Earth. But for the vast majority of the time and space, we do not have any data available. And numerical models can help us understand what was the thermal and geological evolution in the past. And if the model is physically consistent, we can also understand what the Earth's physical condition was in the past. And another reasoning for that is that many surface processes, for example, the melt generation at the mid-oceanic ridges, the mountain building at the oceanic trenches, and the earthquakes, they can be linked to the deep interior. And that interior is not accessible directly to us. But we can use numerical models, and we can use those models which are constrained with the observed geophysical data so that these models are physically consistent and we can use the surface data to understand what is happening in the deep interior. And one such data which I will use today is the seismic tomography, and that is the difference in arrival time and of a phase at various stations. And this is a non-unique problem. That is, if we have a low velocity anomaly here and we look at the arrival times at the surface, the same arrival times can be explained by having a low velocity here and here. But the advances in computation and the also advances in data deployment has led to several updated tomography models which are unique and can give us a clear idea of what is happening inside the Earth. So the recent tomography models are well resolved enough that we can use it to convert it into appropriate physical conditions of the Earth. And the way the seismic tomography is used in physical conditions of the Earth is that if we look at the temperature, the regions that are low velocities, for example here, the regions that are fast, seismically fast, for example in the slabs, are also the regions that are cold or have lower temperatures. And regions that are seismically slow are also the regions that have high temperatures, that is plume. So we know that there is an inverse relationship between the seismic velocities and the temperature. So higher the temperature, lower the seismic velocity, and vice versa. For chemical composition, this relationship is not very direct. For example, if we look at the profile of different chemical compositions with depth, this is garnet, spinel, and this is the ISP model. Different chemical compositions can either increase or decrease the velocity with respect to our reference model, depending on the depth. So the relationship between the chemical composition and the observed velocity anomalies is not so clear, and it can either increase or decrease the S and P wave anomalies. So using all this information I just shared with you, the overall workflow for my models is that we will set up these models which use seismic tomography, and the seismic tomography would be used to infer the physical like temperature and density distribution, and also the rheology, which is how the material is defined or how it deforms under acting forces. And using these numerical models, which are constrained by observables, we will compute the surface velocities and the stress state in our model. So first, I want to discuss the global mantle flow models. And this is the work I'm doing with my postdoc advisors, Juliana Danberg and Wendy Gassmuller at the University of Florida. And what I mean by global mantle flow models is what we just briefly discussed. So if we look at the VS distribution or the tomography data, and this tomography is a global tomography, so you can see it goes from surface to the core mantle boundary. The regions that are seismically slow can be interpreted into regions that are further. So for example, here, the red regions which are slower are also regions that have higher temperatures. And consequently, the regions that are higher temperatures are also the regions that can be interpreted as low density. So the red regions here represent regions of low density. And what we do essentially is we use the seismic tomography model and convert it into equivalent buoyant forces. And these buoyancy forces come from the different density distributions in the Earth. And that generates an instantaneous mantle flow field, which creates the stresses and the velocities we are modeling. We have several existing global mantle flow models. For example, if we look in the top left, this is the model by Cambridge Globe, and they're all trying to, the models I show here are trying to model the observed surface velocities and match it with the GPS velocities. And we see that they get a reasonable fit. So what is new in my study? One thing which they have not considered is that if we want to have plate-like deformation, we need to prescribe regions that are weaker than the surrounding lithosphere so that the plates can slide with respect to each other. Because if the regions are the same density, then they are the same strength, then there is no weakness that can be concentrated and the plates would not be able to move. So all these models prescribe plate geometries or the regions where plates are weaker with respect to the surrounding lithosphere. And if you look at the geometries here, these geometries are all based on NUMERICAL model, which is from 1990s. So even the recent mantle flow model in 2022, they use this NUMERICAL plate boundary model. And we know that since then, several updates have come and advances have come in the plate geometry models. And this is the model by Peter Bird, which shows the inclusion of several microplates, and also in the checked regions, the diffuse deformation, where the plates are very difficult to map, or a single Euler pole is difficult to define. And one of the questions I want to ask with my global mantle flow models is the influence of a different plate boundary model on the surface motion. So not using the novel model, but a more advanced model, and how does it affect the model surface velocities? And if we look at another area of these global mantle flow models, so as I mentioned, the interplay between these forces lead to the observed surface deformation. And there have been several studies to understand what is the force contribution, or which force is more dominant in generating the observed surface motions. So Conrad and Litko-Bertolini, they suggested that slab pull force, which is the pull that is coming from the slab as the slabs are going down, contributes to about 60 to 70% of the total plate motion. And the rest comes from the slab suction, which is the lower mantle forces, or the buoyancy forces that are generated from the converted tomography into density, equivalent density contrast. But another study by Stadler in 2010, they suggest that lower mantle doesn't play as much role, and most of the plate boundary surface plate motions can be explained by just using slab pull at the mantle transition zone. And the reasoning for that is that the model near the surface is better than the global tomography model, because global tomography model are usually diffused. So this diffuse tomography is converted into equivalent, more resistive forces, and that reduces the speed of the slabs, or the speed of the plates. That's why they suggest that if we have slabs only until mantle transition zone, that would give us the best fit to the observed surface motions. On the other hand, Anthony Tutu in 2018, this is a group in Postdoc, and they suggest that 70% of the force comes from lower mantle alone, which is a lot different from what this group suggested. So there's a lot of discrepancy in the contributing forces which generate the surface plate motions. So another question which I want to answer through my models is, what is the relative balance of plate tectonic forces that generate the observed surface motions? In order to do that, I start with the global tomography data, and this is has both P-wave and S-wave global tomography. And in this figure, I'm showing the low velocity regions in red, so the plumes, and the high velocity regions in blue, the slabs. And these velocity anomalies are converted into equivalent temperatures by different scalings at different depths. So the high or the low velocity regions or plumes are converted into high velocity regions in the temperature field. And conversely, for the high velocity regions or the slabs, they're converted to low temperature. But near the surface, because the tomography is so diffused in the lower mantle, or as you go deeper, I use a different model. And the reasoning for that is that this model has more consistent information with regard to the location of slabs and also the cooling of oceanic lithosphere. So at the mid-oceanic ridges, it has lower temperatures, and at cratons, it has, at the mid-oceanic ridges, it has higher temperatures, and at the slabs, it has lower temperatures, and similarly with cratons. And because we know that cratons are not denser than the surrounding lithosphere, I also make it neutrally buoyant, which means that the density contrast with respect to the surrounding lithosphere is not included at the locations of cratons. So based on this temperature field, I also compute density field, and the density from tomography or at depths below 200 kilometers, they come from the S-wave tomography, and it has a different scaling factor at different depths. And this profile is based on inversion of geoid, and this is the inversion which is done by Steinberg and Calderwood. And this is consistent with the surface observation of geoid. And using this density scaling, I get the equivalent density field. So regions which have plumes are also the regions that are less dense, and the slabs are denser. And near the surface, as I said, so in the top 200 kilometers, I use a different density contrast. So I use a constant thermal expansivity and then compute the densities based on the temperature perturbations. And the viscosity, or how the material deforms, comes from another reference viscosity profile, and this viscosity profile is also based on Steinberger and Calderwood, so it comes from the geoid observation. And you can see that this is the one-dimensional profile with depth. But because we want to include lateral variations in viscosities, what we do is that whatever there are lateral variations at a particular layer, we scale them to this 1D profile so that there are lateral variations, but it is still consistent with the observed geoid inverted profile. And then, as I mentioned, we also prescribe weak zones where we use the plate model. So here it is a novel model, and this region is weaker. So if, the darker values represent lower viscosities, and this region is, in this case, about three orders of magnitude weaker than the surrounding atmosphere. And this setup determines the viscous forces or the resisting forces in the model. But once we had the density profile, that determines the buoyancy or how the material is driven in our model. So using that, we compute the, we set up these models in aspect, and we discretize our model. The way we discretize it is using adaptive mesh refinement. The reason for that is that the refinement is more finer near the surface where there is a lot of heterogeneity and not so fine as you go deeper. So near the plate boundaries, because this model is continuous, we use a certain thickness of plate boundaries. And in this case, it is about 50 kilometers, which is in terms of a Gaussian. So it changes smoothly from the center to the surroundings. And the cell size is about 15 kilometers or 16 kilometers. And we solve for the equations of momentum and mass with the prescribed temperatures we compute from the tomography and another model near the surface. So running these models, we also we use this model and then we change the friction, because what we want to do is we want to find a model configuration that gives us the model velocities consistent with the GPS velocity. And in order to do that, we change the frictional forces along the falls. So that determines how easily the plate can slide with respect to each other. And also the asthenosphere viscosity that determines the mantle drag. So if you have a lithosphere sliding over an asthenosphere, that determines how much drag forces there are. So lower the asthenosphere viscosity, more easily the plate can slide over the asthenosphere. And we choose several values of both viscosity and asthenosphere viscosity to do our parameter study. And we want to find a model that gives us a velocity configuration that is most similar to the observed GPS data.
Where are you going to ask a question? You said friction, but the model is completely viscous, right?
Yeah, but frictional forces. So it's not, you're right, in the sense that I'm not describing a friction because there's no plasticity in it, but it's just lower viscosity with respect to the surrounding atmosphere. Okay. Yeah, yeah. So the resisting forces in the plate. And we choose different plate boundary models. So because our goal was to see the effect of using a different plate boundary geometry than the novel or the simplified plate boundary geometry. So we tried 4 different models. This is the novel model, which is the most simplified one. And this is what the community uses in the global mantle flow models. This model has vertical, it does not have dip information, so it's only vertical weakness that is prescribed. And we use another model, which is the Peter Bird's model, and it includes the additional microplates. And this is also a model which includes vertical falls or vertical plate boundaries. But there's an updated model which is based on the seismicity, or how the earthquakes happen. And this is the GEM model, or global earthquake model. And in addition to the vertical like plate boundaries, it also has these diffuse zones where the deformation is very complex. But these diffuse zones, they only extend in the crustal depths because that's where the seismicity is observed here. And this model also has dip information. So if the slab is subducting here along east direction, the plate dip is also along east, just to be consistent. And then we use another model which is based on the GEM model, or the global earthquake model, which only includes the plate boundaries which are discrete and does not have any diffuse deformation zone or any crustal faults. So it has weakness which only extends through the lithosphere and which is discrete. Another difference you could notice is that both bird gem and gem models, they are not closed. So they do not form closed polygon, which is formed by the Novell and bird closed models, and which is what we've been using so far. But these models are not closed. For example, here there is noticeable difference where you do not have, because these models are not based on GPS data where you require a plate to be closed and have one Euler pole. These models are open where you see maximum seismicity, or where you see maximum seismicity. So based on the parameters of viscosity of falls and asthenosphere and the plate boundary model, we compute the residual for our model velocities with respect to the GPS data with three measures. The first one is the angular correlation, which only measures the directional fit with the GPS value. So a value of 1 would imply perfect fit to the observations, and the value of -1 would imply a negative fit, like the vector is pointing in this direction, but the model value is pointing in the opposite direction. And then we also compute the residual for just the speeds of the plates. So without including any directional fit, if the speed of the velocity matches the speed of the GPS data, this is we use this residual to quantify that. And then we also compute the velocity residual, which includes both direction and speed fit. So for our first parameter study with just viscosity of falls and asthenosphere, we fix a plate boundary model. So here we use bird closed boundary model, and we change the plate boundary viscosity. So from left to right, we increase the plate boundary viscosity, and from bottom to top, we increase the asthenosphere viscosity. And notice that I'm using two color scales, but in both color scales, the lower values or the lighter colors represents regions that have good fit with GPS values. So as you go down and left, which is if you reduce the asthenosphere viscosity and reduce the plate boundary viscosity, so you're reducing the resisting forces. The plates move really fast, and you see the plate residuals to be high everywhere. Like that's why the colors are so dark. And as you fix a plate boundary viscosity and increase the asthenosphere viscosity, there is more drag force at the base of the lithosphere, and the residuals increase a little bit. But the more we see a higher influence of changing the plate boundary viscosity versus changing the asthenosphere viscosity. What I mean is that as we increase the plate boundary viscosity by an order of magnitude, so we go from left to right, the residual change a lot compared to if we change it by an order of magnitude for an asthenosphere viscosity. So we go from here to here. And because it is at a different interval, it would be one model, alternate model. Nevertheless, we find a best fit models which have intermediate plate boundary viscosity, so viscosity of 1e20, and low asthenosphere viscosity, so 5e to the power 17 to 1e to the power 18. And if we increase the plate boundary viscosity more, then we see almost no change in the residual. So the plate boundary viscosity, plate velocities, they look very similar without any influence of the asthenosphere viscosity. And the reason is that the friction between the plate boundaries is so high that the plates cannot slide past each other. So the observed residuals are just the negative of GPS data we have. And using this calculation and using the best fit models here, we select different configurations near the plate boundary viscosities because we know that plate boundary viscosity has more effect. And then we change the model for different plate boundary geometries. So here, each column represents the different plate boundary geometries we just discussed. And each row has a different measure of residual. So we discussed three measures: angular correlation, speed residual, and velocity residual. I'm sorry, this should be velocity. The circles represent the residual at a particular plate boundary viscosity and asthenosphere viscosity. And the lighter colors in each subplot represents models which have good fit with the observed GPS data. And I'm also showing you the maximum value for each subplot. So what I want to say here is that we get angular fits of about 93% with the observed GPS data, and we get speed residuals which are close to 1 centimeters per year for our models. And another thing we see is that if you look at just the directional fit, the directional fit always increases as we go higher in plate boundary viscosity and lower in asthenosphere viscosity. So going from left to right, the directional fit improves for each plate boundary model, and going from top to bottom also it increases. But for the speeds are somewhat intermediate in the plate boundary viscosity, because as we go higher than a particular value, the plates have too much resisting forces, and that's why the residual is high, but the sweet spot is observed around 1 to 2.5 e to the power 20. And because the velocity residual includes both speeds and direction, we use the models that have lowest velocity residual for each plate boundary geometry, and we try to analyze them. So here are the best fit models with different fault viscosity and asthenosphere viscosity, but for each plate boundary geometry. So Nouvelle, which is the simplified model, the bird-close model, which has more microplates, and the GEM model, which has the diffuse zones and also the angular information. And then the bird GEM model, which does not have the diffuse zones. And one thing you notice here is that, so again, the lighter colors are the regions which have low residuals, and the darker colors are the regions that have high residuals. So one thing you would notice is that different plates perform differently based on the plate boundary geometry we have employed. For example, in the Nouvelle model, the Pacific plate fits really well, but not so well for the other plates. And in the bird GEM and GEM models, the North American plate fits well, and additionally in GEM model, the Eurasian plate fits well too with the observations. Overall, we see that the GEM model, which is the most advanced model in terms of the plate boundary geometry we have, gives us the lowest fit out of all these plate boundary computations. And we can also see that using comparing their angular correlations. So just looking at the directional fits.
I have a, with all these arrows, what is the model exactly? I mean, how do you just reference to some frame or
it's a
frame or
for the velocity?
Yeah.
It's absolute plate motion. So the model name is IPRF 2008. It's like Streamer. Oh, it has no net rotation exactly. So the sum of all rotations from each plate is 0. So this will give different. You're right. This will give different values if we fix something. But both in our models and in our GPS data, we are using no net rotation, so that removes the uncertainty of using a different frame of reference with respect to the plate. Yeah.
So the motion is not measured relative to
Any
hotspot plane.
Yeah.
Not nor distant star. It is something else. I mean, when we say as a whole, all the plates are moving at a certain speed, but with respect to one, that can be, I think, still a question.
So I think hotspot reference frame gives very similar results to a non-net rotation frame.
Okay.
So I'm not certain if the hotspot reference frame is much different from this, but it's not with respect to any plate.
Oh, okay. No net rotation, that's the only constraint.
Right. I see you're not convinced.
Talk a little bit again about this kind of spatial heterogeneity in the fits. They're just these huge spots that are kind of black that seem to affect the results a lot.
Right, yeah.
So it was also
previously it looked like the Noodle performed the forest, right?
Right.
Now you're saying that this one has very high, low angular correlation.
And also high velocity residual. And it does perform. So I am showing you just the best fit model. So the model that corresponds to this value of plate boundary viscosity and asthenosphere viscosity for each plate boundary.
Sir, would it make sense somehow to normalize it by how much spatial area is fit well. If we go back to the previous picture, right? If you just have, are you proportionally penalized if there is a very dark spot on your map here? Let's say you're fitting all of the plates well, but there's just one microplate that you fully know what it would look like in your global analysis. Would you say this is a good model or a bad model?
So we do use residuals with respect to the, so the residuals are normalized with respect to the area. So what I mean is that it's equal area residual, which means that near the equator, it contributes more than values near the pole.
So in that sense, you do actually account for the size of the plates.
Right,
You
but
kinda wanna
not
give
the
specific flavor.
magnitude, yeah.
Don't have rotation at plate area. Yeah, no angular.
Oh yes, Bob can explain more on the plate. Yeah. But we do not, so our angular fits are normalized by the observed GPS velocity. So these values, they give better fit if specific plate, for example, fits better than the rest of the plates, but not for our velocity residual. And we choose the best fit model based on the velocity residual because it incorporates both magnitudes. So choosing the best fit model for each plate boundary geometry, what we find is that the GEM model, it performs best. And we can also look at the angular correlation for all of these models, which is how good the directional fit is. And these are the same values as I showed in the last graph, but in a bar chart, which makes it easier to see. And the lighter colors representing better model fit are the models that is the model that corresponds to the GEM model. So for our first question, which we asked, the influence of plate boundary geometry, what we find out is that based on a result of GEM models fitting better than the other models, or especially the closed plate boundary models, we conclude that the plate boundaries in reality are not uniformly weak, and there are regions of plate boundaries that are stronger with respect to the other regions of the same plate boundary. So next, we take our best fit model, which is the GEM model. And here again, the arrows represent the residuals. So because the Pacific plate is slower than the observed GPS values, it's pointing in the opposite direction. But the colors represent the plates with better fit. And our GEM model, the best fit model, includes heterogeneity in the top 200 kilometers, where we use a better definition of lithospheric structure and slabs and mid-oceanic ridges. And it also includes the tomography model that has a diffused heterogeneity in the lower, below 200 kilometers. But in order to understand the contributions from different parts of this model, we selectively remove different contributions. So first we remove the contributions that come from the tomography. And what it shows us is that the effect only from the slabs which are defined in the top 200 kilometers and the lithospheric structure on the surface motions. So running this model with an adiabatic mantle without any lateral heterogeneity, we can isolate these force contributions. The second configuration we choose is we remove the better definition of slabs near the Earth's surface. So in the top 200 kilometers, we remove the slabs and whatever low velocity regions, for example, the ridge structure is near the 200 kilometers. And effectively, what it does is that it only includes contribution from the diffuse tomography at the lower depths, and it isolates the effect of flap pull near the surface on the surface motion. And lastly, we take another model which has a homogeneous lithospheric structure. So it does not have lithospheric heterogeneity, but instead have one density and one viscosity for the lithosphere everywhere. And additionally, it has slab pull near in 200 kilometers, in top 200 kilometers, and also diffused tomography in the lowermost mantle, or below 200 kilometers. And what this model does, it isolates the effect of lithospheric structure and also the buoyancy difference between oceanic and lithospheric plates. Because now the lithosphere is one density only, so the continental density, continental lithosphere is same density as oceanic lithosphere. And what we do is that based on these modified configurations of our best fit model, we compute the average velocity from each of these models and divide it by a reference model, which is the best fit model. So the HM tomography is the homogeneous tomography model that has homogeneous structure below 200 kilometers. And this bar chart represents the contribution that comes only from the top 200 kilometers. So what it shows is that the plate speeds on average are 73% reproduced if we have the lithospheric structure and the slab pull near the surface. And the plate motions on the surface, the colors here they represent the point-wise difference. So how does this variation change along different plate boundaries is what is shown here. So bluish color represents regions where the plates are slowed most, and the whiter regions are plates which are not so affected by removing the lithospheric or by removing the tomography structure. And so we can already infer that about a quarter of the forces are driven through the buoyancy forces or density differences below 200 kilometers, or that comes from the diffuse tomography data. And next, we also look at the slab removal. So what we do is we remove all the high definition of slabs near the surface in top 200 kilometers. And that explains, so the contributions we have are only from the diffuse tomography and the lithospheric structure. And we find about 40% of plate speeds with respect to our reference model that includes all these contributions. And if we look at the surface or lateral distribution across different plates, the slowest plates are the ones which are oceanic plates. So for example, Pacific, Nazca, Cocos, Australian, with the exception of African plate, but here the ridge push is also removed. So removing the heterogeneity near the surface affects a lot more than removing the heterogeneity at deeper Earth, or that comes from the tomography, which is more diffused. Because now we can only explain 40% of the observed plate speeds. And next, if we don't have any lithospheric structure or a lithosphere is same, there is no difference in density between continental and lithospheric, continental and oceanic lithosphere, the subduction would not initiate. So even though we have slabs and we have tomography data, this model gives us only 12% of the observed speed in a reference model. And we can conclude now with the different contributions of plate forces that the increased basal drag that comes from a lithosphere which is constant thickness and the absence of any buoyancy difference between ocean and continent affects our plates the most. And lastly, I also compare our reference model with the global strain rate model. So these are the computed strain rates at the surface, and on the right are the global strain rate models, with magenta colors representing high strain rates and white colors representing no strain rates. And notice that within the plate interior, where there are no recordings or there's no data in the observations, we still have low strain rates. And we can identify 3 zones. The first zone is this very high deformation along the discrete plate boundaries that also corresponds with the very high deformation in the observed global strain rate model. And then we also notice the intermediate strain rate in the diffuse deformation zones, north of India, here, and also in the Western US and the Western African plate. No, excuse me, South American plate. And this is the zone which has intermediate strain rates, and it just the inclusion of crustal faults, so not the lithospheric scale faults, but the diffuse deformation zone in the plate boundaries, it affects our strain rates. And I really want you to remember this point because it is relevant for the next part of the talk. And lastly, the third zone, which is the interplate zone, which we still have some strain rate, but these are lower compared to the surrounding regions. And there are no strain rates here, but because our model is continuum, we still have low strain rate in the model. But you can see the correlation between the observations and our model very clearly. So in summary, when we asked ourselves if there is an influence of plate boundary model on the surface motions, we find that the best fit model is not actually the one which has close plate boundaries, but which has most advanced crustal faults and also lithospheric faults, which is the gem plate boundaries, and that fits best with respect to the other plate boundary models. And yes, there is an influence. And we conclude that also the presence of diffuse deformation zones or continental crustal faults represent more realistic distribution of plate boundaries rather than discrete closed polygons. And we also asked what is the relative balance of plate tectonic forces that generate the observed surface deformation. And we find out that the buoyancy difference between lithospheric plate and oceanic plate is most important to generate slab pull or to initiate any subduction, and therefore it influences the surface motion the most. So for the second part of my talk, I want to talk about the seismicity in central and southeastern US due to upper mantle heterogeneity. And this is the work I did on my dissertation with Unso Choi and Chris Powell at the SEISMIC. The motivation for our work was the observed tomography in the central and eastern US. And this was a study, a regional tomography study by Burial in 2016. And what they found out was a very large positive anomaly across a cross-section AA prime, which is passing through like just south of New Madrid seismic zone and crossing Eastern Tennessee seismic zone. And this large positive feature was also observed in the other global tomography model. So it's not an artifact, but we can see it in a diffused form in other global tomography models also. And the question we wanted to ask is if the local mantle heterogeneity we see in the tomography controls the present day crustal seismicity. And the workflow for our models is we start off with the observed tomography and we convert it into equivalent temperatures. And using those temperatures, we set up our model with equivalent buoyancy forces and equivalent viscosity distribution. And again, we run our models in aspect. So this is the viscosity distribution that is shown for our model with the surface seismicity in red dots. And the gray contour shows the large positive P-wave anomaly features observed by Burial. And we set up our model so that the resolution is consistent with the tomography data resolution. We compute 3 geodynamic fields. First is the dynamic topography. And what I mean by that is that in the absence of any mantle flow, we assume the topography we see at the Earth to be isostatic. So any deviation from the isostatic component is the dynamic topography, is the flow due to the motion of the material. So if we have hot point material rising up, it would elevate the Earth's surface. And if we have cold dense material going down, it would depress the surface topography. And this change with respect to the isostatic component is the dynamic topography. And it is related with the radial stresses because the material is going in the direction perpendicular to the surface, so radially. And we also compute rate of change of dynamic topography. We do that by running the models forward in time and then taking the difference between the dynamic topography. We also compute gravitational potential energy. And what it means is that crust having a different distribution in density and in structure, and lithosphere having a different lateral density and structural heterogeneity, we assume a depth of compensation where the gravitational potential energy is calculated. So what it tells us is the stresses generated due to change in lateral densities and structural heterogeneity. Based on all these 3 geodynamic quantities on our model, we compare each quantity with the observed seismic distribution or observed earthquake distribution. So the red dots are the epicentral locations, and the lighter colors are the regions which have high value of each of the geodynamic quantity. So for a dynamic topography, we see some correlation of high dynamic topography with earthquake density in South Carolina seismic zone and also here. But we don't see much correlation of rate of change of dynamic topography with the observed earthquake distribution. But on the other hand, we see a good correlation of gravitational potential energy with the regions of high earthquake density. So based on this, we compute the scale of each geodynamic quantity. And as we can see, there is small positive correlation of dynamic topography with the earthquake distribution and quite a significant relationship with respect to the observed earthquake density. And these values, they represent 0.5 value represent a perfect correlation. So this scale represents about 0.23 scale of GPE, which is the lateral variations in density and structural heterogeneity affecting this affecting the earthquake distribution. We also compare our model stresses with the observed stresses. So here in the colors are these modeled fault types. So going from thrust to normal faulting from west to east. And the gray lines represent our modeled maximum horizontal stress direction. And the blue lines represent the observed maximum horizontal stress direction. And except for Eastern Tennessee seismic zone, we see a good correlation between our model and the observed maximum horizontal stress directions. And we think that for Eastern Tennessee seismic zone, our model does not perform as well because it maybe we need other complication like compositional heterogeneity included in our models to explain the seismicity in this region. And we also use a reference model to generate other model configurations. So this is a reference model that includes a reference area band and also contributions from tomography. And then we assume a hypothetical laterally homogeneous mantle and also a hypothetical model which has no lithospheric root. So that what we are looking at is just the contributions from all the upper mantle heterogeneity and only the positive root which Periol saw in the tomography studies. And using these models, we compute two more indicators. One is the differential stress, the difference between the maximum and minimum stress direction. And Coulomb stresses, which is given a fault plane, what is the likelihood for a fault to slip given a stress state? And looking at the scale for these model configuration, we see positive scale for both differential and Coulomb stresses for the model that has all the upper mantle heterogeneity, but not for the model that only has lithospheric root, which suggests that the earlier idea with having a lithospheric root concentrating all the stresses is not shown by our models. And in summary, if the upper mantle heterogeneity concentrates stresses and lead to earthquake generation in central and eastern US, we show from our models that yes, there is a positive correlation between the lateral density variation to the observed seismicity on the surface at central and eastern US. So just to conclude my talk, we compute the current physical and geological state of the Earth that would give us the best fit with the observed GPS data. And we also find that the upper mantle heterogeneity concentrates stresses at the pre-existing fault in central and eastern US, promoting earthquake generation. And as a way forward, there are still some questions which we don't know, like how can we generate the fault weaknesses consistently? So for our models, we have to prescribe the fault and generate plate-like deformation. But ideally, we would want to generate them self-consistently in a time-dependent manner. And how can we use these models which are consistent with the present-day observations and go back in time to infer the past physical state of the Earth? And lastly, how can we integrate these regional and global tomography models into one single model? So that concludes my talk, and thank you for your attention. This is a
Let me ask a really stupid question. One might have. It's related to the zero rotation. I was wondering, has anyone calculated how much moon induces flow in the mantle?
The slab model?
The moon.
The moon.
There's
Oh,
tides,
sorry.
and so there's a tidal bulge. It's always lagged and behind where the moon is because of viscosity. And so there Earth is slowing down, and like the Earth, but that must make it a net flow.
Mm.
Well, I don't know how large it's going to be. You viscosity guys, people.
We don't even know if all the different parts are rotating in heat. And or in the inner core.
Oh, but you can start with this ball.
There must be a way to estimate it, but since I've been a beginner, first came up with that idea that tidal force by that component or gravity is the driving force for continental drift, but it has been completely rejected. In terms of magnitude, definitely it's not as great as to driving forces, but doesn't mean that it has zero effect. So I think it's so much work, but I personally don't know how strong it can.
Yeah, I don't know, but that's an interesting idea.
I do have actually similar, maybe stupid idea. We have a centrifugal force, and then that magnitude changes, with latitude. But we always, must be small. But over the long term, can it be really just ignored? That's one idea, but I didn't have a chance.
So all these convection models are in a
Non-rotating, right? So it's all radial. There's no ellipticity.
Eventually, it's gonna slow down and the moon is gonna go around one side of the Earth will always stay at the same time.
Can you go back to your slide 40? Or wait, no, the one where you start maybe 41, the seismicity. So of this portion, so the results are that you get a good match, something matched well in the, or in,
So
I think there were two conflicting things, right? So you were matching the horizontal stress orientations. That looked good, except for the Eastern Tennessee assignment. But something else looked really good in the Eastern Tennessee,
the
right?
gravitational potential energy.
Okay, that's
Right.
GPE. Okay.
Yeah.
So
So
what does it mean? That's not mentioned really.
So gravitational potential energy, because it is more influenced by relationspheric structure and density, we think that is appropriately, we have enough information, or at least that part is incorporated correctly in our models, but maybe the viscous deformation or the viscosity conversion is not so well included in our models for Eastern Tennessee cyclone. So how the material is deforming, we might be a little bit off from reality.
For the seismicity, I guess you're probably more worried about the horizontal stress orientations, yeah. Or
So we did this comparison to see how good our model is with respect to the observed effect observation, observed maximum horizontal strength directions.
or asked differently, would these faults slip in the modeled stress field? It looks
No,
like
no.
they're perpendicular to the dominant fabric there, right?
Right, so we don't have faults in our model. We assume a geometry and compute the stress state for that fault state. We don't have faults in our
No,
model.
sure. I mean, they're not in the model, but I'm just saying theoretically, right?
Yeah.
You superimpose the fault strikes for Tennessee and these gray
Mhm.
lines, it would not be optimally oriented for split.
Right.
So is it? I mean, I guess the seismic implications are not entirely clear. I guess, even though it mentions some things, but yeah, necessarily.
I mean, it's possible that this observation is a little bit off too. Like,
Lewandowski, right? He used spoken mechanism.
the
Or is it moral breakout?
you can look at it again.
Pretty sure it's spoken mechanism.
Yeah.
we have a good quote back in the
No. There are pieces.
Why not? Let's, I mean,
Local mechanism.
just not enough coverage. Not enough, I mean, it's like a hard.
Chris is working on it.
In Eastern Tennessee or also in
Steve Morgan did a good local mechanism study for humanity, but that was its finite timeline. We don't have them. Let's our earthquakes are very small. It's not as trivial.
No, sure, yeah. It's getting very common.
So where are we at let the plate geometry self-organize, or what is the term? That let them emerge as a result of all these dynamics. So how successful are we now?
So, I mean, you might know of the Australian group that claims that the plate reconstruction to 1 billion.
1 billion years.
Yeah, I don't know how much we can believe that, because the oceanic lithosphere can only be so much thick before it subducts.
Mm-hmm.
So before 200 million years ago, we don't really know much about the plate reconstruction or how the current plate geometry evolves.
Mm-hmm. But if we start from a certain initial condition, like throw the Earth, whatever, then let it evolve thermally and dynamically.
Yeah.
Then is there any hope that we end up with the current state?
Maybe, because there is a group in you like Becker, Thorsten Becker students. They are trying to develop self-consistent CT ridge systems, and they're very close to it. So I mean, that's already a big step, that you can have nothing from the beginning of Earth and then develop these ridge systems just based on the heterogeneity effect the Earth. But as for all the plate geometries, I'm not sure how far we are. But it seems like we are still a little bit ways ahead.
Let's do it.